So last time we got to the point where we were going to start talking about nomenclature of ethers. Remember, this is a new functionality that we were starting, and we kind of defined what made something an ether, and I'm trying to get it focused. So I don't know whether it's focused well on there. And so once we define the ether, which is basically, we had an organic residue attached to, or two organic residues attached to an oxygen atom. And we said that that organic residue, there's some flexibility on whether it was primary, secondary, tertiary, alkyl group. We could have vinyl groups. We could have aryl groups. So there are a lot of things that fall under that category. But how do we name them? Well, ethers are a subordinate functionality, just like we saw, remember, with alkyl halides. And that means basically that there are different ways of naming them. You can name them where they are, in fact, the functional group that is primary, but often they're also named as substituents more frequently than other functionalities are. So think about the example of alkyl halides, whether we could either say methyl iodide for the name or iodomethane, where it was either the parent functional group or a substituent. And I don't know whether it's on yours, but I don't think that we're focused very well here, and I'm not. Let me see if I can get the focus in better. Well, it may just be my screen. All right, so how do we name them? The first thing is acyclic. Okay, and as I said, there are two ways that we can do this. The first of those ways is you simply identify the organic residues on either side of the oxygen, and then you add the word ether to them. So it's actually three words. It's the two organic residues followed by the word ether. So identify the two organic residues bonded to the oxygen, and then add the word ether. Okay, and so an example of that would be this. So looking at this acyclic ether, we can see that there are two organic residues attached to the oxygen. So we look at the two residues. We know that this is an ethyl, right? And this is a methyl. And so all we do is put these, of course, in alphabetical order. So we'd say the name is ethyl methyl ether. So that's a pretty simple way of naming the compound. Another example, just to reinforce this, remember the residues can even be vinyl or aryl. So let's say that you have this ether. We'll notice that this organic residue here is a vinyl group. So this is vinyl, which is our archaic name for it, or it could be ethynyl if you chose to use the IUPAC. And then this is ethyl. So alphabetically, ethyl comes first. So ethyl, vinyl, ether. And just to emphasize, because we've transitioned from the last lecture, what if we had one of the residues be an aryl group? And let's do a alkyl substituent there. So again, we have the two organic residues attached to an oxygen. So to name this, this is phenyl. Remember when we talked about the substituent name for benzene? Phenyl, iberylite from Faraday. And then this is a T-butyl, right? And so then alphabetically to put those together, it's T-butyl phenyl ether. Okay? So if the ether linkage is the only functionality present in the molecule, it's often the way you name it, simply naming the residues and then putting the word ether at the end. But there's another way of naming these where you have typically other functional groups present that may be more important. And then you're going to name these as alkoxy alkanes. And so your ether linkage is going to basically be now a substituent name, is all this means. So, if more than one functional group is present, ether is usually subordinate. And you name it with the other functional group being the parent. So for example, if we had this compound where I'm going to put a double bond here, so we have alkene functionality in that ring. And let's put a T-butyl group over here. And so, sure, I could name this using the first way, where I would just name this residue and this residue and put the word ether. But now that I have this double bond here, let's just say that I want to name it as the alkene. And so to do that, remembering our rules, we number this cycloalkene like this. One of these carbons has to be 1, and then we want the substituent to have the lowest number, so we number in this direction. And then we would name this ether linkage here as a substituent now, okay? And the substituent name is basically to take what would be the alkane name. So, this is a T-butane, really, or T-butyl. But what we do is we change the suffix in the substituent name to oxy, all right? And so I know that you can rewind on this because I'm erasing, but we can still write the name. So that substituent becomes T-but. Instead of butyl, or if it were an alkane, ane, I add oxy. So it's D-butoxy. And that indicates, that oxy indicates that there is an oxygen that this alkyl portion is attached to. And so therefore the name of my molecule, remember that was in the 4 position. So it's 4-T-butoxy. And then I'm naming it as the cycloalkene. So it's cyclohexene. The 1 is understood. If you wanted to put 1 cyclohexene, you could, because the double bond is in the 1 position, but it is by rule. And so it's understood. So if you understand that it's 1, you can leave it as being understood. Okay? So that's how we would do that. Now, what about cyclic ethers? Have to think about them a little differently. Okay? Cyclic ethers come in different forms, and the main one we're going to talk about is epoxides. We're going to talk a lot about the cyclic ethers that qualify as epoxides, and when we're talking about nomenclature. Cyclic ether nomenclature not as important if it's not an epoxide. So epoxide nomenclature. There are basically 2 ways of naming epoxides also. Remember, in general, epoxides are where you have this functional component. This is the simplest epoxide, but you can certainly have an epoxide present as a structural component of a larger molecule. So how would we name this? The first is using what we call oxide nomenclature. And in oxide nomenclature, what we're basically looking at is adding the word oxide as a separate word after the name of the alkene that is oxidized to form it. Okay, because if you remember, we talked about epoxides last semester. It was one of the reactions that we talked about of alkenes, where you did an oxidation with peroxy acid, and you could convert an alkene into the epoxide. And so basically this nomenclature technique is based on what alkene you would oxidize. So you're almost looking at a retrosynthetic type analysis on your epoxide to get the name. So looking at the simplest case, okay, this would be called, if I was using the oxide nomenclature, so that's the second word, ethylene oxide, because this epoxide is made from ethylene. Okay, this is oxidized to give that epoxide, so ethylene oxide. And so how about this one? How would I name this? Well, again, you're thinking, what alkene was this epoxide made from? What was oxidized to give this? It would be that alkene. That would give me this product on oxidation. Therefore, using the oxide nomenclature, this would be cyclohexene oxide. Okay, so that's pretty straightforward, and that's one method of naming it, called oxide method. But the other is to treat it as a substituent, and this is a little bit trickier to get your head around, but once you do, it's pretty straightforward, and that is using epoxy as a substituent name. Now that makes sense because we said that ethers as a substituent, you use this oxy nomenclature anyway, but this is epoxy. Okay, and so the thing to remember here is you're treating the whole epoxide as a substituent. So you're thinking about it as one unit, just the same as if it were a methyl group. Okay, but what makes it different is there are actually two bonds that come from your parent chain that would, define this structural unit. And so you have to treat both of the C to O bonds that are attached to the molecule as the same substituent. Okay? Treat them as the same substituent. So, commit this to memory, of course, but you really need an example to see exactly what I mean here. So let's look at the example. Let's say you have this epoxide. And I'm putting in the H's on these carbons just for clarity when you're looking at it for the first time, so you can make sure that the stereochemistry is how you want it. And then I'm going to put in a substituent down here, and let's just make it a methyl for fun. Okay? And so if I'm treating this as one substituent, so that oxygen is a substituent, but both of these CO bonds, they're on different carbons in the ring, but they're considered, just one substituent. And so when I'm doing the least sums on this, I am going to number like this. And I know you're experienced enough on nomenclature where I don't have to identify to you why that is the lowest sum, but it is, counting in this direction. That gets me the lowest number for the substituents. But this is, even though its location is 1, 2, it's considered one substituent. So because of that, this one substituent and this one substituent are related to each other how? Remember, when you have two substituents on a ring, you can use the simple cis-trans nomenclature. So these are trans to each other, right? So I would say this is trans, and then alphabetically, epoxy and methyl, so the epoxy comes first. And so location, I say 1, 2, epoxy. But I'm treating that really as one substituent that requires two location designations. Okay? And then my methyl group is in the 4 position, so 4 methyl cyclohexane. Okay? Substituent name. Okay? And that's a cyclic example, but you do it the same way if your epoxide was acyclic. For example, if we started with this. So now the only thing that's cyclic in this molecule is the epoxide. Other than that, I just have this alkyl chain. And let's throw, just for fun, let's throw this ether linkage in there to make it fun. Okay? And so how would I name this now? Well, it's acyclic, so now I'm looking at the longest continuous chain to be the parent, right, which is right here. And I'd start numbering on this end. So 1, 2, 3. Now notice 2 location designations, but 1 substituent. 1, 2, 3, 4, 5, 6 is my parent chain. And so I have a substituent here, and I have a substituent here. Okay, this one is epoxy, and this one is methoxy, right? Because it's a substituent that's an ether, right? And so I know my locations, I know epoxy comes first, but here it's acyclic. So there's not a cis and trans in relation to these two substituents, but there is a cis and trans in terms of the epoxide, right? This group and this group, if you're looking in terms of the attachment of the epoxide, these two groups are cis to each other, right? So this is a cis location 2, 3 epoxy, right? And then it's 4 methoxy hexane. Okay? So cyclic, you're looking at how the epoxy substituent is related to other substituents. That gives you cis and trans. If it's an acyclic epoxide like this, you're just looking at how the residues attached to the epoxide are related to each other. Okay? We don't really talk, as I said, about nomenclature of normal cyclic ethers. It's just not something that, you know, because there are like 6 different ways of doing it, and it's just not something that we're going to concentrate on. So if in your textbook it talks about naming cyclic ethers, just normal ethers, don't worry about it. We're only doing acyclic ethers and then epoxides. Okay? And so that brings us to structure and properties of ethers. We're transitioning into where we can talk about reactions of ethers. But remember, we've talked about nomenclature now. I'm going to talk a little bit about structure. That's going to lead to reactivity. But then we're going to do preparation of ethers and then do the reaction. So structure and properties of ethers. Okay, now, you know, we don't have to go a lot in this. Ethers are really related. Remember how we talked about the fact that alcohols were closely related to water structurally? It's the same thing. Ethers are related to water in a way because you're basically just replacing the H on an alcohol with another alkyl residue. And so structurally, they're very similar. So if you're looking at it in terms of structure, you have your oxygen, which has two lone pairs, and now two organic residues. So it's in a bent shape, which means it does have a net dipole, just like you would see for water or for alcohol. And so that means that structurally and in terms of reactivity and properties, they're kind of similar, okay? And so one of the main properties of ethers is also one of the reactions, and that is the main property is that these ethers react readily with oxygen. Just oxygen in the air, and so I'm going to say air. And so if you have a bottle of ether and you take the lid off, it's going to be interacting with the oxygen that's in the air. When it does that, it'll oxidize. And it'll oxidize to, I'm going to just say air, but we know that that's the oxygen that's in the air. You will oxidize these to this, which is what? A peroxide. Explosive. Peroxides explode like a bomb. Okay? Not at the levels of like if you have hydrogen peroxide in your bathroom, don't worry, the bottle's not going to explode. But if you have a high concentration of peroxide, it actually explodes by shock. So just bumping into it can cause the explosion. And so this is an important thing to remember because here you have your ether, okay? And that ether, if not stored properly, over time can air oxidize and become a peroxide. So then your bottle of ether will slowly build up a concentration of peroxide. So then you have an explosive molecule sitting within a bottle of very flammable material. Okay, because ethers are very flammable. And so is that a good thing? No. And so that's why you notice that when we use ether, it always comes out of the refrigerator. We store the ether sealed and in the refrigerator to keep this air oxidation from occurring. If you ever run into a really old bottle of ether that's just been sitting on a shelf, be careful with it. In fact, when we moved from the old building on campus into the newer building we're in now, there were a couple bottles like that on the shelf of really old ether that were in a storeroom. And I actually got a really long ruler and I would poke the bottles from a distance just to make sure that they wouldn't explode before I went and touched them. Okay, so that's a property to remember. All right, so before we get to the reactions of ethers, we want to talk about how to prepare them. Now the good news is, we'll see that a lot this semester. The good news is, just like we saw with alcohols, we already have talked about some reactions that form ethers. So not all of these are new. Some of these are review. Okay, but let's start with the new one. Under the category of preparation of ethers. The first reaction is called the Williamson ether synthesis. Yeah, so it was developed in a time, they used to name reactions after people that developed them. They don't anymore. All right, and so the ether synthesis that Williamson came up with was basically taking an alcohol and you convert it into the alkoxide salt. And we're going to talk about that in a second, how you accomplish that. And you react this with an alkyl halide. Let's just use methyl iodide to make it simple. And you can see this reaction is really not anything that we wouldn't be able to predict without being shown this, because we have an alkyl halide and we have what? A nucleophile. This is just an SN2 reaction, okay? Because the nucleophile is going to react with the electrophilic center of the alkyl halide and displace the iodide. This is good old-fashioned SN2, right? And that would give us this substitution, this substitution product, right, where the nucleophile has substituted for the halide, and then your counterion would just be associated then with the leaving group, potassium iodide. So just a really straightforward, simple SN2 reaction that gives an ether as the product. Now, if it's SN2, it's going to have some limitations, right? So the Williamson ether synthesis has the limitation that it works best with primary alkyl halides. So whatever your alkoxy nucleophile is reacting with, it's going to work best when it's a primary alkyl halide. Because if you go to secondary or tertiary, then you bring in E2 eliminations. And so the reaction becomes less efficient and useful. So you're really pretty much limited to primary alkyl halides. Now, how do we make the alkoxide? I'm not sure whether this is review or not, so I want to show you. You make these from the alcohol. So if you wanted to do a Williamson ether synthesis, you'd first have to make that alkoxy anion. And to do that, you react an alcohol with a metal hydride, like potassium hydride. It would also work for sodium hydride. You would just be changing the counterion, because what happens then is you simply remove the acidic proton here, and your metal becomes the counterion, and then you're going to form H2 gas, okay, because your two H's. And so you're giving off hydrogen gas, okay? And you can do that, it works with potassium or sodium. So that's just a simple way of making that, okay? Now what happens if, as I said, just to emphasize, when you're reacting this then with the alkyl halide, it's primary alkyl halides that you can react these alkoxides with to form your ether, okay? And so with that in mind, and you're thinking about preparation of ethers, how would you go about making this ether? If this was your target ether in a synthesis, how are you going to make this? Well, basically what you're looking at is using the Williamson ether synthesis. I can imagine cleaving this on either side of the oxygen, meaning that either this is going to be the alkoxide carbon, or this is going to be the alkoxide carbon, or this is going to be the alkyl halide, or this is going to be the alkyl halide, because those are the two pieces, alkoxide coming together with an alkyl halide. So how would you make the judgment? When you're looking at that, think of it in terms of the alkyl halide. If this were my alkyl halide, it would be secondary. If this were my alkyl halide, it would be primary. So which one do you want to be the alkyl halide portion, the one that's primary? So when I do a retrosynthetic analysis of this, I would want to react this as the alkoxide and this as the alkyl halide. Okay, so you see how you do that? You're analyzing the pieces. All right, if they were both primary, then it doesn't make any difference which way you do it. It'd be totally up to you. All right. Another way of doing the Williamson that's a little bit different, and that is using a phenol. So let's say making phenol ethers. The reactivity is a little different, but not much. And that is a phenol, remember, was one of those things we said is a little different than an alcohol in its reactivity. But we can take phenols and make ethers in a pretty straightforward fashion. We can just treat it with a simple base. It doesn't have to be, a metal hydride. It can just be sodium hydroxide, for example, followed by, again, a primary alkyl halide, and we can in fact form this phenolic ether like that. Okay, very closely related to the Williamson. So that's a new reaction in application, but it's certainly not anything new. We've seen SN2 reactions of this fashion before. But now here's one that's review. You may not remember, but we learned a reaction last semester on alkenes that gave ether linkage. Okay, and it was alkoxymercuration. Okay, and if you remember, this was related to oxymercuration. With oxymercuration, that was the one where we added water across the double bond, and it went Markovnikov anti. But we also said, if you change the water to an alcohol, then you can add the alcohol across the double bond, again, Markovnikov anti, and the result is an ether linkage. Okay, so just to remind you in general, you have your alkene, and I'm going to react it. Remember the reagent for oxymercuration, which we revisited when we talked about preparing alcohols a few lectures ago. We use this mercury acetate, right? But now instead of water, we're going to use an alcohol. So now this alcohol is going to be what adds across the double bond, but still anti and Markovnikov. And then you follow it up, remember, with the sodium borohydride. So the same reagents for oxymercuration, but you are now using an alcohol. And so when it adds across that double bond, remember it's the pi bond that's breaking, so you're basically adding your H and your OR across the double bond, and you end up with that ether linkage. Okay? Now, one that might be a good specific example if you're thinking about what goes on a flashcard. So example. Let's use this alkene, and I'm going to treat it with mercury acetate. And let's do ethanol as the alcohol, followed by sodium borohydride. And so I'm going to be adding this alcohol across the double bond, Markovnikov anti. In this case, neither one of those things matters because I'm basically just going to add the ethyl group onto the ring. Okay, and so stereochemistry isn't really even important to show there. But what would happen if I used, through the magic of digital lecturing, I'm just going to add the methyl group on there. Now, of course, in your notes, you're going to want to redraw, but let's put this methyl group. Because remember, that's the one that we like to use for our flashcards. So if I do this, this brings up the whole idea of regio and stereochemistry, because if this is adding in a Markovnikov fashion, that means that it's going to add to the same carbon as the methyl, because that is the more substituted side, because my H is added to the less substituted side. Okay? Now, the mechanism for this, you already know, because you studied it last semester. So we don't have to revisit the mechanism, you know it, but we do want to talk about limitation. There is one limitation to this reaction. It's actually very versatile. Unlike the Williamson ether synthesis that required the alkyl halide to to be primary. With this alkoxymercuration, the alcohol that you're adding to the alkene can be primary, secondary, or tertiary. The only limitation is you cannot form di-tertiary ethers. Di-tertiary ethers. And a di-tertiary ether would be something like this, where the residue attached to this side of the oxygen, that's a tertiary center, right? And the residue, the carbon attached on this side, is also tertiary. You can't make a di-tertiary ether, okay? But you can, if I took that methyl group off, I could make that. And again, one of these would be the alkene, and the other one would be the alcohol that you're adding across, and you can do it virtually in either direction. It doesn't matter which residue was the alkene and which was the alcohol in most cases. Okay, so that's a really versatile reaction. Okay, so two good ways of preparing ethers. One of them was new in a sense, but it was a similar SN2 reaction that we've seen before, and then now alkoxymercuration we've already seen. So two good ways of making ethers. So now that brings us to reactions of ethers. Now there's some good news at this point. Ethers are inert to most reagents. They're not very reactive. So the good news is there are not a lot of reactions. We're going to see in a minute that epoxides are different because epoxides are reactive. So they have some more reactions. But ethers themselves, not very reactive at all. Okay? They are inert to a lot of things. So ethers are inert to halogens, mild acids, bases, and kind of redundant, nucleophiles, because nucleophiles are bases, bases are nucleophiles. So just to make sure you know that there's no kind of basic cleavage that could happen or no kind of substitution with a nucleophile. So I'm listing those separate. So ethers are inert to all these things. And what you might notice on this list is one of them, I put mild acid. So inert to mild acid. That makes you kind of believe, why did he say mild acids? Because ethers are not inert to strong acids. Okay? And so the first reaction, and really one of the only we'll talk about, is ethers are cleaved by strong acids. Okay, and so HI, which is a strong mineral acid, is the most common. So if you want to cleave an ether, HI is your first choice. HBr works, okay, but HCl does not. So, I mean, when we say strong acid, that means strong acid, okay? And so what would the general reaction look like? Let me start with a simple example. Okay, so here's my ether linkage of my two residues. And I'm going to treat this with HI. And usually you need to heat it. Remember, we use this triangle to demonstrate heat. And it's going to cleave, and when it cleaves, it forms an alkyl halide, and an alcohol. And so I know when I was learning this, back when we carved this stuff out of stone, I thought about this as it's really the reverse of a Corliss-Williamson ether synthesis, right? Because I'm going back to an alkyl halide and an alcohol. And trust me, if you think about it that way, you're going to see how important, because it tells you something about, you know, how it actually cleaves also. Because there's just one set of cleavage products that form, okay? Because watch this, I can take this phenolic ether and treat it, let's use HBr here and heat, because we know HBr works also, and it's going to cleave, and it's going to cleave to the alcohol plus the alkyl halide. You see that? It's the opposite of a Williamson ether synthesis, okay? And so what is the regiochemistry here? Of the cleavage. It works just like a Williamson. Notice that when you cleave, you're cleaving to get the primary alkyl halide. The alcohol can be whatever, but notice that it's cleaving to give the primary alkyl halide, and that's because this cleavage is occurring also in an SN2 manner. Okay, and so the mechanism is going to help explain this to us. Okay, because when we're talking about stereochemistry of cleavage, we're talking about which side the cleavage occurs on. So in other words, which side does the, you know, either the I minus or the Br minus attack to facilitate the cleavage. And so if I were to draw an ether like this, let's put a big one on here just for fun. And what I'm doing here is I'm exaggerating the difference. Here's my ether, here are my two residues, okay? And these two residues have different degrees of substitution on them, right? And so when you talk about regiochemistry of cleavage, what we're talking about is which side does the nucleophile react with to afford the cleavage. So it's the position of attack. And so there's one set of choices that occurs if you've got a primary or secondary alkyl ether, which is basically saying that your residues on either side of the oxygen are either both primary, both secondary, one primary, one secondary. The only things that are present are primary or secondary. And if that's the case, it's going to react with SN2 regiochemistry. Okay? So that means mechanistically, if I take this and I'm going to react it with HI, okay, I know this is the acid, this is the electrophilic proton, so my nucleophile is the oxygen of the ether. That's going to react out with the H, break that bond and move the electrons to the I. Now, how many times have we seen this? We've seen it with alcohols too, right? We've seen it with water. Anytime you have this oxygen with organic residue and you put it in the presence of an acid, what does it do? It protonates that oxygen. So think about the big picture. We've talked about now, last semester is water. We talked about alcohols and now ethers. It's always the same thing that happens in the presence of an acid. And so I can draw this intermediate now, where that is protonated. And now I also have my I minus. Okay? So now I minus has a choice. Does I minus come in and attack at this center? Or does it come in and attack at this center? Okay, well this is a secondary center, and this is a primary center. So if this reaction is SN2 regiochemistry, that nucleophile is going to go to the less substituted side, right? SN2 works best with primary alkyl halide. So it reacts here, not here. And when it reacts here, it kicks these electrons out to the O. And so it's forming a new bond between the I and this carbon, breaking this C to O bond, moving these electrons to the oxygen. And so by magic of digital recording, you can freeze on that if you need to draw it and think about it, but I'm moving on to what the result of that cleavage is, which would be what? Where you'd end up with this alcohol plus this alkyl halide. Okay? If you have tertiary, so if you have a tertiary or benzylic, okay, which is, which means one of your residues is going to be either tertiary or benzylic. So that would be an example like this. Let's make up one like this. See, one of my residues is tertiary. Once that happens, okay, this is going to react by SM1, E1, because remember those always happen in tandem. And so what does that mean? When I treat it with my HI, okay, the first thing that's going to happen is same thing we saw before. This is the nucleophile, reacts with the electrophilic site on the HI, pushes the electrons out to I. Now you might want to pause that as you're writing it down, but I'm going to erase it to move on because I can draw this intermediate that's formed. And I have this. I think that's what I had, is something like that. And so I had this tertiary center and I had this secondary. And so basically I'm going to spontaneously dissociate, okay, and break this bond, move the electrons to the oxygen, okay. And so when I do that, I'm going to form this alcohol, right? But then over here, I form this carbocation, right? Because I've spontaneously dissociated to get this carbocation. That's why it's SN1E1. And so now I either have the I minus come into this center to form the tertiary alkyl halide, or it could act as a base and pull off this proton and push these electrons in. So I could get either the SN1 or the E1 product, either the alkyl halide or the alkene. Okay, so the reaction is not as clean in that case, but those are the products that form. All right. So moving forward, some examples of cleavage. But what happens now when you have cyclic ethers? Or epoxides. And so we're going to quickly see that epoxides are going to be a different animal. when we're talking about this. So let's first deal with just plain old cyclic ethers. So for example, if I have this ether, okay, now the good news is if you just have a normal cyclic ether, it's going to react exactly like an acyclic ether. No difference. So for example, if I treat this with HBr and heat, it's going to do a cleavage. And when it cleaves, you're going to cleave to the alcohol, 1, 2, 3, 4, counting my carbons. You're going to cleave into the alcohol and the alkyl halide. The only difference is they're attached, they're on either end of the molecule, right? Because it started out as a cyclic system. So when you cleave a cyclic system, you just get one molecule. It just has the dual functionality on the two ends. Reactivity is the same, okay? And so the same things would be true if you had substitution on here. You know, if you put a methyl group on here, right? And you did the cleavage, it's going to, the Br is always going to go to the less substituted side. So secondary versus primary. Same rules. Cyclic ethers behave exactly the same way as an acyclic ether. So there's nothing new there. But what happens when we get to epoxides? Epoxides have different reactivity. So we can almost treat them as their own little functionality, because remember they had their own nomenclature that we talked about earlier, okay? And they're going to have their own set of reactions. But before we get to the reactions of epoxides, we have to review on how we prepare them. So if you want to use an epoxide in your synthesis, first, how do you prepare it? So preparation. And the good news is, this is review. I'm going to write it up here, but it's review. We know how to do it. You use a peroxy acid. So if you remember last semester, we had our alkene, and we would treat it with the peroxy acid. And remember, we always just use the generic. You know, sometimes you saw it as RCO3H, or drawn out like this. It's just a carboxylic acid with an extra O in there. So it's a peroxy acid. And when you do that, it's a concerted mechanism, remember, that gives us this epoxide. Plus it gives you the carboxylic acid as the byproduct, but that's only important if you're doing a mechanism. Okay, now I said it's a concerted mechanism, and the importance of it being a concerted mechanism is what's usually true when we see concerted mechanisms. You usually see a what? You usually see the stereochemistry preserved in the reaction, because you're always adding the things, in this case, from the same side. And so if I had an alkene like this, and I reacted it with my peroxy acid, and by the way, that's always how you will see it on a test. I don't specify what peroxy acid. Just always use an R group. The result of this is what? Your two C to O bonds that form the epoxide always come from the same, or pointing in the same direction, because the addition was concerted from the same side, and so you end up with that product. Okay, now the reason for it is, and I'm going to just briefly show you this mechanism just to demonstrate that it's concerted, but it's not one that I'll probably test you on. It's not that interesting to me. So I'm going to try to draw the peroxy acid. This is the R, carbonyl OOH, and then here's my alkene. And so basically what happens, and I'm going to take this back, this, if you can, erase, because I want to draw this in a little better orientation to what I'm doing. Because basically in a concerted way, you're moving these electrons in, so you're forming a bond between this oxygen and that carbon. And at the same time, you're breaking this pi bond and moving those electrons out. So you're adding this oxygen in a concerted manner. Boom, boom. And then that moves these electrons around and out like this. And so then that OH minus it forms is able to take this proton. Okay, so all of that's happening in a very concerted way. And you'll see when you look at this and slow it down, you'll see that that's actually forming, as a result, the epoxide. But it's also, and I'll put those two bonds there, but it's also forming the carboxylic acid. Okay, so that's what's mechanistically is occurring. Okay, so I guess I have about 5 minutes, so I'm just going to quickly show one more reaction, which is a new reaction, kind of, but it's certainly something we'll recognize. It's a way of making epoxides from the halohydrin compound. Remember, we talked about halohydrins last semester. We formed them from an alkene, reacting it with something like chlorine and water. So remember, if water was present, we actually added, first we formed the chlorinium ion, but then water came in as a nucleophile instead of the second chlorine. And because of that, we formed the halohydrin, and it was Markovnikov addition, and it was anti. So my OH and my Cl end up anti to each other, or trans. And so I can take these then and basically treat it with base, which is aqueous, and basically I end up forming the epoxide. Okay, now we're at a reasonably good stopping point, because what we're going to do next time is we're going to look at this reaction mechanistically, how it's happening. I'm going to give you a little foreshadowing. This is really a Williamson ether synthesis. Okay, but it's on a halohydrin, because the base is going to remove this proton, which will give me that alk oxide, which will then, in an intramolecular way, react from the top side of the carbon that has the leaving chlorine on it. Okay, so that's going to give me the epoxide plus sodium chloride. This is really just a Williamson ether synthesis, but I'm reacting them together to form the epoxide. And so we'll pick it up right here next time and move forward with how to actually do reactions on the epoxide that forms.